Sorry for the interruption. And because of some technical problems, then this is paused for some time. Next one is the Simaruba. Simaruba, or the paradise tree it is called, is an evergreen multi-utility tree of medium size. It is both a source of edible oil and also biofuels. The oil can be used as a cocoa butter substitute, extenders in confectionery and bakery industry. The oil cake is the valued organic manure. The plants are polygynous with the varying percentage of staminate, pistillate, male and the female bisexual flowers in the population. It can grow well in the tropical climate and can withstand scanty to high rainfall. All type of well-drained soil are suitable for the Simaruba cultivation. Origin, Florida, United States. Family, Simarubaceae. Then species Simaruba glauca. Vernacular name is Simaruba paradise tree. Acetuno, the bitter wood. Next is the Mahua. Mahua is one of the important tree species in central India. Mahua is one of the important tree species in Central Asia, Central India, as it produces the abundant deciduous and nutritive flowers. This is used for the edible purpose, either fresh or the dried and stored for the indefinite period. It is fast growing with a 20-meter height. Evergreen tree cultivated in the warm regions of its orangey seeds. Its oil is used by the tribal as a vegetable butter. In addition, it is used in skincare products, soap, detergent, etc. It serves as an important fuel oil, hence a good source of biodiesel. The seed cake is used as manure. The flowers are used to produce an alcoholic drink in the several parts of India. Origin Central and North India. Family Sapotaceae. Then species Madhukai indica. Vernacular name is Mahua, Maura, Ilapai, Hippe in Kannada, and Yapa. And these are the trees, the fruits, and these are the seeds. Kokum. Kokum is an important minor fruit besides seeds. Seed oil source for edible and non-edible application. It is reported to be imported from Zanzibar to India. It is found to be grown widely in the tropical rainforests of the Western Ghats in Konkan, Goa, Southern Karnataka, and Kerala. It is slender, evergreen tree with the dropping branches. Kokum fruit is a promising industrial raw material for the commercial exploitation in view of its interesting chemical constituents. The seed yield a valuable edible fat known as kokum butter, used in the chocolate and confectionery preparations and also in manufacturing of soap, candle, and ointments. It is an important source for the biodiesel. Origin Asia and Africa. The family is Cruciodaceae and species Garcinia indica, and vernacular name is kokum. And actually this is Amsol kokum butter tree, and these are the tree fruits, and actually these are the seeds. Jojoba. This is also a tree. This is a potential tree borne oil seed, and this is grown in northern India, and origin is North America. The family is Simondicaceae and species Simondicaceae chinensis. Vernacular name. This is goat nut, coffee berry, vanilla nut, wild hazel, pig nut. And this is the tree, and these are the fruits, and these are the fruits. And kernel has to be taken from this. Neem is the most common in India. Everyone knows it actually. Neem is one of the most valuable tree species found in India. It can grow on a wide range of soils up to pH 10. Which makes it suitable for every agroclimatic zones except in the high-end cold regions. It has a deeper root system, thus does not compete with the annual crops for the soil moisture. It is multi-purpose tree which provides all the requirements of the rural areas, namely timber, fuel wood, fodder, oil, fertilizer, pest repellents, etc. Neem is known for its azadirachtin in this content, and it has been commercially exploited in many the products like the medicine, manure, pesticide, insecticide, etc. Neem is regarded for its environmental values. Origin is India. The family is Milaceae. The species is Azardic indica. Vernacular name is Neem, Beu, Tamaka, Tamabin, Maragosa tree, Bepu, Nimba, Bepu like this. And these are the tree, and these are the fruits and the seed kernel. Vegetable oils. The oils taken from actually all these seeds are called actually these vegetable oils. Generally, these oils will be removed from these kernels or from the actually sometimes include with the cell and without cell also, and they speech and actually they put in the expeller and with the putting away high pressure that oil is removed from that, and those are called the vegetable oils. Properties of vegetable oils. Vegetable oils and fats are water soluble hydrophobic substances composed of fatty esters and glycerol, triglycerides. Carbon chain length and number of unsaturated bonds varies. Triglyceride having the molecular weight of 800 to 900, 4 times larger than typical diesel. Oxygen molecules present in these vegetable oils. Vegetable oils have high viscosity and density and a low volatility and calorific value. Cetane number from 35 to 45, high carbon residue, high flash point, and there's 220 to 285 degrees Celsius. Calorific value 88 to 94% of the diesel and low sulfur content. Fuel related properties of selected vegetable oils. Fuel related properties of selected vegetable oils. Azadica indica, that's a name. Jatropha, Maduka indica, Pinnata. This is Cumunis. This is nothing but the castor. Rapeseed, soybean, sunflower. All the last 3 are edible in nature, and actually this above all the 5 are the non-edible in nature. And here in the table, some of the important values: iodine value, then cetane number, cloud point, pour point, and flash point, and viscosity in centistrokes, millimeter square per second. Then centistrokes is been given. And for the neem, iodine value is 82 to 98, and then have got a cloud point 286, 4.280. And we are most interested in actually this part of actually this is the oil, and that is the viscosity. Viscosity is a very important property because of having actually such a, this is the viscous, because if you take up a normal diesel, viscosity of the diesel is of the order of actually this is a 1.52, this is a 4.5 or maximum 5 centistrokes, millimeter square per second, and compared to that actually these vegetable oils or nearly 8 to 10 times actually this is more than the diesel. And that too here the castor, we can see this castor is 240.1. It is nearly this is 85 times actually this is more than a diesel. And we can see that these oils are unsuitable for direct use in diesel engine. The reason is that higher the viscosity, more the viscosity, and actually more amount of actually the power loss, the power it requires, or actually pumping power it requires to make the fine actually the spray in combustion chamber. And this is a major difficulty associated with actually these vegetable oils. Comparison of fatty acid composition between the various edible and non-edible vegetable oils. Fatty acids are nothing but the triglycerides. These are bound to be happen to be actually in the vegetable oils. If the free fatty acid is 0, then it does not have any property of converting actually this vegetable oil into a biodiesel. And More actually, this fatty acid composition actually has got a then more ability to convert it to that. This is why it is. And again, actually, this different the oils are there here: fatty acids, palmitic, palmitolic, stearic, oleic, linoleic, linolenic, and all these are having some the chemical references, and we can see that these are the different values of this one. The orcuminous oil contains 89.6% of linoleic acid. Then this one is the linoleic acid. Castor especially. The oil content in seeds and kernels of some non-edible plants. Azardica, the indica, neem tree, percentage of weight in the seed kernel. These are references. Oil contains weight percentage in the seed, 25 to 45 in the seed. Then actually the kernel, that's 30 to 50%. And polonga, 60 to 75, 50, 70, like this rubber. You can see the Maduka indica, Jadropa, and in the seed kernel has got some maximum oil content, and this is the seed put together has got an average of 30 and percentage of oils in this. We can see the mahua, drumstick, tobacco, karanja, castor, soap nut, jojoba, and all these were actually listed, and this is the oil content in percentage by weight. The yields of the various non-edible oil feedstocks. The neem 2,670 kg per hectare. These are the seeds talking of polonga, carbon, rubber, jadropa. sorry. Drumstick, tobacco, karanja, castor, jojoba, tongue, and for all those given here, for among them polonga, we can see 4,680, and karanja is of the order of 900 to the 9,000 kgs per hectare. We can 1 hectare is equal to nearly 2.2, 2.25, 2.5. This is hectares. Derivatives of non-edible oils as diesel fuels. Non-edible vegetable oils can be used as the fuels for diesel engines. The primary problems associated with using the straight these oils as alternative fuel in the combustion ignition engines are caused by very high fuel viscosity and low volatility. Volatility is very low, viscosity is very high. But then it becomes bound to have actually some problems in incomplete combustion, improper combustion in combustion chambers. Either we have to modify the combustion chambers to suit this, then or actually we have to modify the fuel. The high viscosity of non-edible vegetable oils can be reduced by the several techniques, which include dilution, microemulsion, pyrolysis, and transesterification. These are the different techniques of reducing viscosity of non-edible vegetable oils. Among that is the first one is dilution of non-edible vegetable oils. Dilution in the sense actually they take the diesel, then 10%, 20% of this vegetable oils directly you mix with the diesel, and then actually it dilutes the vegetable oil, and actually hardly there is a change in the property of this the diesel. The oil diesel fuel blend is a simple way to reduce the viscosity of non-edible vegetable oil. This method does not require any chemical process. Just mixing and actually we have to do it. A number of researchers have examined the use of blends of conventional diesel fuel with the non-edible vegetable oil such as jadropa, caracas oil, and Pongamia pinnata oil, azardicha indica oil, etc. Using microemulsions for non-edible vegetable oils. Microemulsions are the transparent, thermodynamically stable, colloidal dispersions in which the diameter of the dispersed phase particles is less than 1/4 of the wavelength of visible light. To reduce the viscosity of vegetable oils, microemulsions with the immiscible liquids such as methanol and ethanol and ionic or non-ionic amphiphiles have been studied. They take actually this vegetable oil and the methanol, ethanol, they mix it and thoroughly actually they mix it. Then it forms an actual emulsion. Then call the micro emulsion. Liquid fuels and biodiesel from the non-edible vegetable oils via pyrolysis. The pyrolysis is a process, the heating it to a certain temperature and actually the breaking the constituent molecules of this one, the oil basically, and actually they're removing fatty acids from that. Conversion of vegetable oils using the pyrolysis type reactions presents a promising option for the production of biodiesel fuel. Pyrolysis is the conversion of one substance into another by means of heat or by the heat with the aid of a catalyst. Thermal decomposition of the triglycerides produces the compounds of the classes including alkenes, the alkadines, aromatics, and carboxylic acids. Different types of vegetable oils produce a large differences in the composition of thermally decomposed oil. Biodiesel via transesterification from the non-edible vegetable oils. This is one of the most popular method of actually the production of actually biodiesel. Transesterification is a chemical reaction between a triglyceride and an alcohol. Most methanol or ethanol in the presence of a catalyst and consists of a sequence 3 consecutive reversible reactions where triglycerides are converted into diglycerides and then diglycerides are converted into the monoglycerides followed by the conversion of monoglycerides to glycerol. In each step, an ester is produced and thus the 3 ester molecules are produced from one molecule of triglycerides. If one molecule of actually triglycerides we take up, actually the 3 molecules of esters it produces. I mean, it's the biodiesel it produces. Ethanol is preferred alcohol in the transesterification process compared to the methanol because it is derived from the agricultural products and is renewable and biologically less objectionable in the environment. However, methanol is preferable because of its low cost and its physical and chemical advantages. Polar and the shortest chain alcohol. Triglycerols are esters of long chain carboxylic acids combined with glycerol. Carboxylic this acid R-C 1,4 oxygen hydrogen can be converted into the methyl ester by the action of a transesterification agent. Transesterification of the vegetable oils can be carried out by the 2 ways. First one is the catalytic transesterification and another one is the non-catalytic transesterification methods. Catalytic transesterification method. In this one, 3 molecules of vegetable oil, 3 mole of vegetable oil and 1 mole of this vegetable oil are taken and actually this heated at around 60 to 65 degrees Celsius for an hour, 1 hour, 1.5 hours, depending on actually this is the free fatty acid actually content in the oil and with an this catalyst in that one, and that is called a catalytic transesterification method. Vegetable oils can be transesterified by heating them with a large excess of anhydrous methanol and a catalyst. Transesterification reactions can be categorized by the alkalis, acids, and enzymes. Comparison of various methanolic transesterification method. Acid or alkali catalytic process, reaction temperature is of the order of 303 to 3 and 38. Reaction time taken is from 60 to 360 minutes. The boron, trifluoride, methanol, sodium methoxide catalyzed, non-catalytic supercritical methanol, catalytic supercritical methanol. For all these reaction temperatures is of the first 3 of the reaction temperature is of order of the 300. For other the reaction temperature is of the order of 525 to 550. And the reaction time actually the reduces for these cases 6 to 12 minutes for actually supercritical methanol and actually catalytic supercritical method it is 0.5 to 1.5 minutes. Means directly actually the conversion becomes more easy in this supercritical methanol process. Because this is a continuous process we can do it, but then catalytic we cannot do it continuously because it must be done actually takes nearly 1.5 or 2 hours for conversion. Non-catalytic transesterification methods. There are two basic routes to produce the biodiesel by the non-catalyzed transesterification. These are BIOX co-solvent process and supercritical alcohol process. BIOX is actually the name of an author or actually the scientist actually who invented this process. By co-solvent process, this this oil is actually this converted to the biodiesel. Another is a supercritical actually alcohol process. BIOX co-solvent process uses either tetrahydrofuran (THF) or methyl tert-butyl ether as a co-solvent to generate a one-phase system. The result is a fast reaction on the order of 5 minutes and no catalytic residues in either the ester or the glycerol phase. The THF co-solvent is chosen in part because it has a boiling point very close to that of the methanol. This system requires a rather low operating temperature. For majority of the laboratory cases, actually catalytic type is used instead of using the non-catalytic type, and then we'll be having actually this is a 1.5 to actually this is a 2 liter the flask. Actually this is a this three-way actually this mouth cloth. This is a this one, and the vessel in that one, actually glass vessel. In that one, actually we put actually all this constituent and actually the heat, and for laboratory purpose actually we make it. And this is the most suitable way of actually this making this biodiesel in a laboratory. Summary of catalytic transesterification of some selected non-edible oils. Summary of catalytic transesterification of some selected non-edible oils. Catalyst used is potassium hydroxide, KOH, sodium hydroxide, and pretreatment acid, Pseudomonas cepacia, CH3ONA, pretreatment, SCI, NaOCH3, KOH, and all these are actually this different catalysts, and these are non-edible oils, castor, karanja, jatopa, all listed here, the combination, the respective catalyst, and actually this is the oil. And percentage of actually this catalyst in this one is given 1.511%, like this. It is of the range of this, range of actually 1 to 1.5, actually the percentage, and except this last one. And the temperature is 330, 33, 38. Then you can see these temperature ranges. We have to heat it actually at this temperature with the castor and actually 1.5% of the KOH. Reaction time is 10 minutes, 3 minutes, 1 minute, 1 minute. See, you can see the reaction time is also given. Percentage of the yield, biodiesel, this yield 80.1, 97. You see 97.6 and 98% is a very good actually. This is the then yield, and that's why actually this the catalytic transesterification process is most preferred in laboratories. Comparison between catalytic methanol method and SCM method for the biodiesel from supercritical methods of the biodiesel from vegetable oils by transesterification. Methylating agent methanol, and in SCM method methanol catalyst is alkali here, NaOH or KOH, none here. Reaction temperature 300 to 338, and here 523 to 573. Reaction pressure 0.1 megapascal, 10 to 25. Reaction time 60 to 360, 7 to 15 minutes. Methyl ester yield 96%, 98% is removal for purification, methanol, catalyst, glycerol, soaps. This is the methanol, methyl esters, free fatty, actually acids, methyl esters, the saponified products, the water. This is the smelling from exhaust, soap smell, the sweet smelling. These are the catalytic and actually this is supercritical methods. The comparison with respect to the temperature, pressure, time, yield, catalyst used and all. Among them, supercritical method is the most important, because if you put a vegetable oil directly in a vehicle, then directly from the system, then biodiesel must be available in the form of continuous supply. ASTM standards of maximum allowed quantities in diesel and biodiesel. Standard diesel ASTM D975, biodiesel ASTM D6751. If you are interested, actually you can go to this ASTM and actually the standards D975 diesel. This is for the ASTM D6751 for the biodiesel. Composition SC C10 C21, FAME C1 C12 C22. Kinematic viscosity in millimeters square per second. The centistokes at 313 Kelvin, 1.9 to 4.1. This is 1.9 to actually the 6. Specific gravity 0.85, 0.88. Then flash point 333, 353, 373, 443. You can see that actually there's a flash point temperature of the biodiesel is then even in the standards given is more flash point. And the cloud point 258, 278, 2 is of the same actually the order. Pour point 238, 258, 258, 289, and then water percentage of 1.05, 0.05, same quantity. Carbon 87, 77, the less in the biodiesel. Hydrogen actually 13, 12. This is an ultimate analysis. Ultimate analysis given. Oxygen 0%, 11% in the biodiesel. See, this quantity is very important in actually the combustion process, because along with this biodiesel, this oxygen is available in the form of the oil itself. Inbuilt oxygen is available in the fuel by 10 to 11%, and then reaction becomes actually very fast. The catching of the fire, the beginning of the combustion takes much quicker than actually the diesel at the beginning, because inbuilt oxygen is available in the fuel. And sulfur 0.05, 0.05, CTA number 40 to 55, 48 to the 60, HFRR the 685, 314, and other things are important. Fuel related properties of biodiesel from non-edible oils. Fuel related properties of the biodiesel. Fuel related properties of actually vegetable oils we have taken up and actually we have studied earlier. Right now, here is the fuel related properties of biodiesel. After the biodiesel, then castor, jatopa, karanja, kusum, mahua, neem, rubber, rice bran, all these are the oils. And actually the density, we can see this 80, 886, 888, 89, 850, 916, 890, 892, 872. CTA number 53, 51 to 52, then 41, 7, 42. 48, 51. It is of the order of actually this. Then cloud point, and this is the cloud point. This is the pour point, and we can see flash point. Flash point is generally higher than actually the diesel, and this makes actually this biodiesel safely can be stored in a cell container or in this anywhere, because it's the fire hazard. Is chances of the fire hazard is very less because of the high flash point. And the problem is with actually this is the viscosity with the vegetable oils we have seen there. It is of the order of nearly 10 times, 10 to 12 times greater for the vegetable oils. But if it is converted into the biodiesels, and then it is of the order of the diesel only it comes. It is of the order of actually less than 5, 10, around that. You can see this here. Castor, the toll, then 4.8 Jojo. Jatopa, Karanja 6.8, 9.2, 3. Mahua, neem, rubber, rice bran, all these we can see this. It is of less than actually the 10, and almost suitable for direct actually combustion into the firing into the combustion chamber, because the diesel is at the order of actually the 4.1 millimeters square per second centistokes, and this also actually the will do it. But in some cases actually the viscosity is even a little higher. And calorific values in megajoules per kg, we can see this, and a calorific value is of this order 39, 38, 40. The diesel is having 42, 43 actual megajoules per kg, and the calorific value is of the order of 0.95, 0.92, 92 to 95, 96, and the percentage of actually the diesel. And sulfur content is given, and all other are actually unimportant here. So far what we have taken up is, just let me repeat actually what what we have so far discussed is, first we have taken what is the problems, what is the need of alternate fuels, that to the bioorigin. And from that one, actually, we have seen that what is the problems with the bio, actually, this is the fuels. And what are the different, actually, this is the vegetable trees or the plants available producing non-edible vegetable, this non-edible vegetable oil seeds. And from that one, how to actually convert into an oil. Then oil, what are their properties? How actually those oils are useful in internal combustion engine as fuel. And then we have to remove the actually this is the free fatty acids from that one, and transesterification and other supercritical methods, and catalytic and non-catalytic methods actually we have gone and we reviewed. And after that one, actually upgradation of the fuel property takes place. Then fuel property upgradation is number one. Upgradation is itself is a viscosity. Itself viscosity comes very nearly actually the or closer to the that of the diesel, and it makes possible directly biodiesel. They say the using combustion chambers directly. Now, so far actually this is a review of the literature we have done it. In our college, we have got a wonderful laboratory of this internal combustion engine and biofuels is concerned. And there actually we conduct a lot of experiments. And one of the experiments I conducted the values, and actually I want to present for the young participants. For the experimental work, we are using the engine specification. Engine specification for the experimental work used is Kirloskar AV1 engine, 4-stroke compression ignition, constant speed, vertical water cooled, naturally aspirated the diesel engine, and it is a single cylinder bore having a 80 mm dia stroke 110 mm, swept volume 533 cc, compression ratio 16.5, rated output 3.68 kilowatt at 1500 rpm. This is a 5 HP. Injection nozzle, Micro Bosch 3-hole nozzle, fuel injection pressure 150 bar absolute, injection timing 27 degree before actually the top dead center. The combustion chamber, hemispherical open combustion chamber, inlet valve opens at 4.5 degree before TDC, closes at 35.5 after TDC. Exhaust valve opens 35.5 degree before TDC, closes 4.5 degree after TDC. Dynamometer, Sage Ford AG series eddy current dynamometer, bidirectional, water cooled, load cell for torque, 62 magnetic pickup for speed measurement, smoke meter, Neptune equipment, private limited, Ahmedabad make, light absorptions by the particles, Bosch units, exhaust gas analyzer, Sage Piton make, the dry basis and non-dispersive infrared gas, unburnt hydrocarbon and carbon monoxide. And actually, and we conducted the experiment in the year 2005 or so. Actually, these instruments were available. Now the exhaust gas analyzer in our laboratory is actually well modified, and we have purchased it with the cost of 15 lakhs spending on it. Then AVL 5 gas analyzer we have presented. Other instrumentation, gas flow, water temperature, air flow, water flow, oil flow, and all these are, this is we have used thermocouples, orifice meter, rotor meter, view rate, etc. Experimental program, variable load tests are conducted at 0.37, 0.92, 1.48, 2.03, 2.58, 3.13, and 3.68 kilowatt at 1500 rpm. Injector pressure 150 bar and water outlet temperature of 60 degrees Celsius. Oil and its blends are heated to required temperature, because actually this heating of oil then reduces the viscosity of the oil. That's why actually the oil is heated in experiment. Engine was sufficiently warmed up and stabilized before taking all readings. Performance characteristics, brake thermal efficiency, brake specific fuel consumption, brake specific energy consumption. Emission characteristics we studied in terms of smoke, unburnt hydrocarbon, carbon monoxide, exhaust temperature. C, programming for the data processing. This is a layout of the experimental setup with instrumentation. You can see this diesel engine, and actually there's a peripheral, and this is the devices for the experimental work. photograph of the experimental setup. Now at present, we have got this test engine, and this is not actually 3.8, and this is 7.5 HP, and then within the 5 gas analyzer, we get this a close view of actually this area 5 gas analyzer, and the whole setup is available in our laboratory. If any young, actually this is the scientist, if you want to work and conduct experiments on this IC, so single cylinder or multi-cylinder, you can contact actually this is head of the Department of Mechanical Engineering, and it is most useful for them for conducting R&D activities in our laboratory. Investigations on the different vegetable oils in the test engine. Directly first we are taking the investigations with the vegetable oils, not biodiesel, vegetable oils. Notations used for the oils: jatropha oil, pangami oil, Deccan hemp oil, tobacco seed oil, bitter almond oil. Then actually better performing concentration of oil or blends are based on maximum break thermal efficiency, minimum break specific consumption, and minimum break specific energy consumption, minimum CO unburnt hydrocarbon and exhaust temperature. Comparison of combustion characteristics of vegetable oils in our experiment. Actually, jatropha, pangami, Deccan hemp, tobacco seed, bitter almond diesel is used. Here we got density, viscosity. We can see this viscosity of oils here. I'm talking of actually nearly actually the 10% to 12% of that of diesel. Flash point of the order of 200, 250 or so. The fire point of the order of actually the 250 or so here. And the calorific value or less than actually this is the diesel as expected. And CT number of the order of 42, actually 45, 48, not applicable, not applicable. It's not calculated rather, and actually this is the diesel. And from the experiment, it is observed that all these vegetable oils actually produces the required amount of power it produces. But the problems with actually this one is that these oils emits actually more the smoke and more carbon monoxide, more smoke, more carbon monoxide, NOx emission are higher because these are the raw oil. These raw oil actually this produces. This is more emissions, but with a little lower thermal efficiency. Thermal efficiency is not that of actually the diesel, little lower than that of the diesel. Investigations on esterified oil. Deccan hemp, tobacco oil, bitter almond oils works with a lower performance and higher emissions, reducing emissions and improving performance. Methyl esters of the Deccan hemp, methyl esters of tobacco seed oil, and methyl ester of the bitter almond oil were prepared in the laboratory. And esterification. This esterification is done in the laboratory. This is the fat or the oil, 1000 kgs, 1 mole, 3 mole of actually the methanol, 3 mole of actually the methyl ester biodiesel producers, and actually 1 mole of glycerol actually this is forms. And these are on a chemical then this reaction terms: methanol, methyl ester, and glycerol. Simple representation of transesterification reactions. And this experimental setup has been created in our laboratory during my experimental work, and this is created in the laboratory. And this we have done actually this esterification here, and these are actually this biodiesel, this glycerol. And properties of the Deccan hemp, tobacco seed, and bitter almond oil, methyl esters in comparison with the diesel respective, then neat oils and other esters. The diesel, Deccan hemp oil, methyl esters of Deccan hemp oil. Then we can see this calorific value of the diesel is 42,000. Deccan hemp oil, methyl, this is biodiesel. The biodiesel actually a little this is the improvement in the calorific value, and actually then to compare to actually the Deccan hemp oil. And viscosity, we can see that 3.8, and this is a Deccan oil, neat oil 35.44, but methyl ester of the Deccan oil 4.82, flash point 45, and actually this is 255 for the oil and 144. This is a methyl esters biodiesel. Like this, for all the this is the oils under the test, actually this values have been given. What happened? What happened to actually the so many? Not seen actually this. My God. Harish, just a minute. You display not the you only you want to figures display. That's fine. This agla graph of graph. Sir, like it. Just Characterization of biodiesel. We have taken up and gone through it. Then very unfortunate, these are not displaying this. Performance and emission characteristics of the methyl esters of Deccan oil is compared with those of the methyl esters of the rubber seed oil and methyl ester of mahua oil and found satisfactory. Break thermal efficiency, break specific fuel consumption, specific energy consumption of methyl ester of tobacco seed oil at rated load is well comparable with that of the diesel. Smoke and unburnt hydrocarbons of METO oil at a rated loads are 11.4% lower and 22.22% lower than that of diesel. However, carbon monoxide emission is higher than that of the diesel for the entire range of operation. Performance and emission characteristics of methyl ester of tobacco seed oil are well comparable with that of the methyl esters of rubber seed oil and methyl esters of mahua oil. And in fact, in general, actually, I want to state that then because of this then conversion into the biodiesel, the performance of actually the diesel engine thermal efficiency increases, and also and this is the emissions, this reduces. And only the problem associated with the biodiesel is that the NOx emissions are high. NOx emissions are very high because of actually these two things. One thing is oxygen, inbuilt oxygen content in the biodiesel, and the higher temperature of actually this combustion chamber. Because of these two things, the NOx emissions are higher, because NOx emission depends on the reaction temperature and the percentage of the oxygen available during the combustion process. And the another way of actually this is improving this engine. So here modification of the oil is the one option, and modification of the engine is another option. Modification of the oil, we convert into the biodiesel and we run the engine and actually we burn on. And the another is then modification of the engine itself. Then how to actually modify the engine? Convert this engine into a low heat rejection engine or semi-adiabatic engine. What is a semi-adiabatic engine means? LHR engine, let me discuss first, then later come to the actually this discussion part of it. LHR engine is a semi-adiabatic engine. What we do here, the combustion chamber, piston face, valve faces, all are actually they coated with an then ceramic coating. We do it. We do actually the ceramic coating, and those coating, if you do it during the combustion, the energy is actually stored inside or held up in the combustion chamber itself. It's locked inside the combustion chamber. Because of the higher temperature, actually this is the temperature available in the combustion chamber, the efficient combustion takes place. And whatever the actually this is some percentage of heat that's supposed to actually go to the ambient is actually the stored and lost to the ambient or the cooling system is actually converted into useful mechanical work, and actually efficiency of these engines are much better than compared to the other engines. LHR engines used to reduce the smoke, carbon monoxide, unburnt hydrocarbon emissions because of the efficient combustions. Deccanamp and methyl ester of deccanamp oil is used in LHR, and results are compared with that of diesel. For validating results obtained, they are compared with the works available in the literature. And LHR test engine, surface of the cylinder head, walls, piston faces are machined to 0.3 millimeter depth, coated with a layer of PSZ, partially stabilized zirconia, to the same thickness by heating it up to the boiling point of 2000 degrees Celsius and spraying to the parts with the plasma gun. Photograph of the piston, cylinder head, and with the valves faces coated with the PSZ. Test on LHR engine with the deccanamp oil. Test on the LHR with the methyl ester of deccanamp oil. For validity, results are compared with the works available in the literature. And the conclusions for such engines is that normal diesel engine is modified by insulating the piston face, cylinder head, and valve faces with PSZ using plasma spraying. Brake thermal efficiency of LHR engine, the deccanamp oil, as fuel is 5.67% higher than that of the standard diesel engine rated load. Exhaust emissions like smoke, carbon monoxide, unburnt hydrocarbon, and deccanamp oil in the LHR engine, the rated loads are respectively 19.1 higher, 28.5% higher, and 61.11% the lower than that of the diesel in the normal engine. Brake thermal efficiency of LHR engine with the methyl ester of deccanamp oil at a rated load is 6.1% higher than that of the diesel in the standard engine. Exhaust emissions like smoke, carbon monoxide, unburnt hydrocarbon for methyl esters of the deccanamp oil in LHR engine at the rated loads are respectively given by the 66, 71, and 88% lower than that of the diesel in normal engine. Performance and emission characteristics of LHR engine with the deccanamp oil and methyl ester of the deccanamp oil are well comparable with that of Jatropha. Volumetric efficiency of LHR engine is lower than that of the normal diesel engine because of the higher temperature, and it affects the density of the combustion product. Investigations on actually the dual fuel engine. Dual fuel engine in the sense, then what we can do is either methanol and ethylene both are used as the primary fuels, and the deccanamp oil as a pilot fuel in the diesel engine. The results are compared with that of the diesel used as pilot fuel. Further, the results are compared with the similar work available in the literature for validity. And comparison of properties of the diesel, deccanamp, methanol, and ethanol, and given here. Then we can see this is the viscosity 553. Then methanol, then ethanol. Deccanamp oil is used, not methyl ester deccanamp oil. Viscosity, cetane number, flash point, heat of vaporization, that then in kilojoules per kg, and this is the ethanol 900, methanol, then actually this is 1110. Dual fuel engine is actually this manufactured, modified into in our laboratory itself. This is an intact manifold. Actually, this is in the intact manifold. Directly, this ethanol and methanol are injected using a carburetor used for the Hero Honda, and that experiment setup has been modified, and actually this experiment is conducted in our laboratory in our college. Properties of deccanamp oil, methanol, and ethanol are compared with that of diesel. It is observed that the density, calorific value, and Cetane number of methanol and ethanol are lower, and heat of vaporization is higher than that of diesel. The existing standard diesel engine is modified and converted into the dual fuel engine. Brake thermal efficiency increases with increase in amount of the methanol share for the Deccan hemp oil and the diesel. The maximum thermal efficiency of the dual fuel engine with the Deccan hemp oil as a pilot fuel, and then is 29.64% against 31.82% of that of diesel, and this occurs at about 45% of methanol energy share. Smoke emission reduces with increase in the methanol energy share. At a maximum thermal efficiency condition, smoke emission for the Deccan hemp oil and the diesel are reduced by 62 and 72% respectively than that of the neat oil. Carbon monoxide emissions first reduces and then increases with increase in the methanol energy share. Maximum CO emissions for the Deccan hemp oil and the diesel are 70 and 57% lower than that of the neat oils. And unburned hydrocarbon, actually this emission and other losses are also reduced. And nowadays, actually, this is the one more the parameter is actually this considered for analysis of the engine combustion. That is called the combustion characteristics. That is called the combustion characteristics. Generally, this is the performance of an engine we measure with the either brake thermal efficiency, specific fuel consumption, and the emissions. And emission characteristics and performance characteristics we call. Another is the combustion characteristics. Combustion characteristics are nothing but it is a theoretical and then prediction of the behavior of the engine, how actually it takes, how then pressure varies inside the combustion chamber. And it depends on that. How actually the pressure is measured in the combustion chamber by putting actually this is piezoelectric then pressure transducer. The pressure inside the combustion is detected, and pressure versus the crank angle diagram we can do it using then actually this pressure and actually crank angle dimensions. Then we can predict actually the temperature then variation in the combustion chamber and percentage of fuel burnt in the combustion chamber. Then actually pressure rise, percentage of the fuel burnt. Like this, so many things can be actually this heat release rate, how much amount of the heat, because the heat release rate is directly proportional to the quantity of the fuel burn. It means by knowing having actually P theta diagram itself, from that so many actually the data can be taken up and actually predicted theoretically or actually in the simulation actually we are doing it. Then the simulation we can compare with our this is the combustion. That's a combustion that is happening in a combustion chamber. And this is similar to the X-ray and some other things here. We do know then X-ray scanning and so many reports of a human being similar to that one. Actually, this combustion characteristics are useful for actually this predicting what is happening in the combustion chamber. In present investigation, the first derivative of the pressure is calculated using the following equation, where n is the specific time or crank angle, is the pressure corresponding to the crank angle n, and h is the interval between values. For DI engine, the cylindrical contents are a single open system, and heat release rate is calculated by applying the first of thermodynamics using the following equation: dq n by d theta is equal to gamma by gamma minus 1 p dv by d theta plus n by gamma minus 1 v dp by d theta. P is the pressure, P is the cylinder pressure, V is the cylinder volume, and gamma is the Cp by Cv, the ratio of the specific heats. And from this one, we can calculate what is the quantity of heat release rate. And these are some of the important this combustion characteristics graphs. Cylinder pressures versus the crank angle. How the cylinder pressure varies for the diesel 100 blue one, and this red one is biodiesel 100%, and another one is biodiesel 95%, diethyl ether 5%. Biodiesel with the 5% of diethyl ether is used in this experimental work, and that has been taken up. Diethyl ether is added to improve actually this is the combustion qualities of actually the biodiesel. And from this one, and using the formula given in the previous actually this, and we can calculate net heat release rate. This is the net heat release rate. From this one, we can predict actually then how the combustion taking place inside the combustion chamber. This is the smoke emission, the smoke versus the brake power, and for the diesel, biodiesel, and biodiesel with 95% with the ether with the 5%, and their effect has been actually this is the given and projected in this graph. And for the smoke emission, the diesel is lower for all the load. Actually, this is under test. Biodiesel actually is more. By adding the ether, the emissions have been actually considerably actually reduced in the smoke emission. Then hydrocarbon, actually this is the emissions, and hydrocarbon emissions are very low by adding actually the ether. And carbon monoxide, and we can see that actually the NOx emissions can be considerably reduced by adding the ether by the 5%, and brake thermal efficiency is actually improved because actually the losses are reduced, and that actually supports for the complete combustion and efficient combustion of the fuel in the combustion chamber. Ultimately, this actually increases brake thermal efficiency. Then the important conclusions of actually this seminar, or actually this slot of this lecture, is that edible plant oil fuels presented do not compete economically with the petroleum-based fuels because they are more expensive. But due to the recent increase in the petroleum prices and uncertainties concerning petroleum availability, there is a renewed interest in the non-edible plant oil fuels for diesel engine. And non-edible plant oils are, first one is edible plant oil fuels presented do not compete because petroleum and actually these prices are and uncertainties are there. Recent increase in the petroleum, and even actually this is the edible oil plants do not compete economically with these petroleum-based fuels because they are more expensive. But due to the recent increase in the petroleum price and uncertainties concerning petroleum availability, there is a renewed interest in the non-edible plant oil fuels for the diesel engine. And actually, the first, it is peanut oil is used in the diesel engine by the Rudolf Diesel, as we know. And at that time, actually, this is the oil cost was very high. And the another major problem is that was an edible oil. Edible oil actually, if used for for running a diesel engine, then there is a shortage of actually this is food for the mankind available on the world, on the planet. And now again, actually, this petroleum prices has been increased, and because of this increased petroleum, this is the prices, and again there is some interest actually is created to go for the non-edible oil plants as a fuel for the diesel engine. That's what actually we have so far. It's gone through and reviewed. Next one is non-edible plant oils are unsuitable for human food because of the presence of some toxic components. These plants are easily available in developing countries and are very economical comparable to the edible plant oils. Biodiesel produced from the non-edible plant oils has a good potential as an alternative diesel fuel. And because of the availability of the huge, actually, this barren land available in some of the countries, and we can grow actually this non-edible vegetable oil plants we can grow, or tree we can grow, and we can collect the seeds, convert into the oil and respective biodiesels, and that can be used because by this non-edible oils we cannot use it because of its toxic nature, and the human cannot actually use it. However, as a serious drawback, most non-edible oils contains a high content of free fatty acids, which increases the biodiesel production cost. More the quantity of FFA, and more will be the production cost, because the free fatty acid has to be removed from the oil. This photograph is taken from one of the tweets of the Prime Minister. Prime Minister Narendra Modi addresses the Climate Summit at the United Nations headquarters in New York on September 23rd, 2019. And in that one, actually, he stated like this: we must accept that if we have to overcome a serious challenge like climate change, then what we are doing at the moment is just not enough. I will conclude actually this session with the statement given by the Honorable Prime Minister. And thanks for the patience hearing all the time. And now the session is open for the discussion. Let me go to the chat. Actually, some 3 questions are there in that one.
Now open for discussion. Just ask the question, participants.
Sir, good afternoon, sir.
Good afternoon, ma'am.
Yeah, good afternoon. Sir, as you were discussing, the comparative study done with various vegetable oils. So many factors you're discussing. So in that, the viscosity and the flash point. So is there, with regard to viscosity and flash point, is there any optimal range which in turn dictates the efficiency of this biofuel that as a safe fuel?
Yes, true, ma'am. Instead of actually the flash point, the viscosity is the main important point. In fact,
okay.
Viscosity directly affects the formation of jet formation, droplet sizes, penetration, and formation of the core inside the combustion chamber. All these the physical properties of the droplet is affected, and ultimately it affects the vaporization of a droplet. And this is the one thing. And then little actually this is the effect of even higher flash point is also there, because of that property it cannot catch the fire immediately. There is a
Okay, thank you, sir.
Thank you. Sir, which ingredient chemical composition point is important in ethanol extraction from?
Hello, sir.
Sir, Dinesh Dhande, and you asked a question. Sir, which ingredients chemical composition point of view is important for the ethanol extraction from feedstock? How ethanol yield is increased? I'm very sorry. I'm from the vegetable, purely vegetable oil side, and now actually now I will take actually this information and question, and actually tomorrow let me answer you by return mail. Please, Harish sir, please collect actually this Dinesh Dande's this mail. Answer back.
Sir,
Hello, sir.
Hello.
Hello, sir.
Hello.
Hello, sir.
Hello. Hello.
Hello, sir.
Hello. Hello. Hello, sir.
Ask the question.
Ask the question.
Okay.
Sir, namaste.
Namaste.
Sir, at a one time, one question, sir. Please.
Sir,
I have a question, sir. Ask.
Vegetable oils being derived from vegetable seeds or whatever it is, their shelf life is a problem. Okay, their shelf life is hardly months. How do you address this problem when commercial value?
What life? If it is a tree borrow, if you take the tree borrow,
You can't store vegetable fuel
storing
as long
is
as diesel.
storing is a problem, because actually it
Yeah.
gets oxidized. It
Yeah.
gets oxidized, it becomes a thicken and all. And that is why actually this we are converting into the biodiesel. And biodiesel we can store for actually this in little longer period than actually the neat oil. And however, anyway actually at present we have got and then production is very low. Production rate is very low compared to actually this is the usage. And the whatever we produce immediately actually we are using at present.
Sir, once commercially, if it is viable,
Once
then
it is
you-
commercial viable, then what happens now? Continuous process. Then if you put the vegetable oil directly by using the supercritical methods, directly then biodiesel must come at the bottom.
I doubt that the fuel should come with an expiry date because it is derived from vegetable oil.
Right, sir. Actually, within the expiry date only we have to use it.
Oh. Thank you.
Thank you, sir.
Sir, this is Vikas, sir. Vikas Anakal from Gulbarga.
Tell me,
Sir,
please.
my question is, sir, for IC engines and other engines, wherever diesel is used, we need some modifications because of this compressed ratio and injection time and injection pressure. How about the other equipments like power generators and all? Are there any modifications required when we are using biodiesel?
No, you look at this now. There are two concepts. One is either modify this is the oil, or upgrade the oil, or modify actually the property of the oil, or actually modify the engine. There are two things. And wherever we are modifying the oil, we are converting into the biodiesel and upgrading actually this is the combustion characteristics of those liquid fuels. We need not actually go for a change in the engine. The same engine, whatever the engine uses, actually the normal diesel, the biodiesel can be used. And engine modification, if you go for, then actually go for LHR engine, dual fuel mode, actually this is the multi-fuel engines like that. You have to go for. As far as actually even your genset can be used, biodiesel can be used in the genset also. No problem.
Okay, thank you.
Ask the question.
Any more questions, please? Now, thanks for giving cooperation and patience listening of this nearly 1.5 hour lectures on this vegetable oils and their derivatives, the combustion chamber and internal combustion engines. Now, I actually thank this organizing of this ATAL 1 week FDP for giving me an opportunity to actually share my views on this biofuels and vegetable oils. And I hand over actually the mic back to the coordinator, Dr. Session2.
Thank you, sir. Your wonderful talk on this biofuel and alternate fuels. Thank you very much. And I conclude this session. And third session will start on the 2:30 exactly. Sharply have to join. Thank you very much, one and all.